Hi there. During our last class, we talked about the mean, median, and mode, and I think we also did the mid-range as well. So I think we're starting here with what can you say about the mean and median for the following examples. So there are two examples here. The first one is rank by sales of selected statistic books, and the values for the rank are here. So to find, so if we want to find the mean and median for this variable, which is rank by sales, we would use a calculator, and my calculator's already on. To find the mean and median, I think we may have done this before in class, but okay, we're going to do it again. We go to Stat and Edit, and I'm going to put the data in list 1. So the data here is listed. So I put each data value and pressed enter each time. It's in list 1. There are 5 data values, and I'm checking, and those are the 5 data values. So I'm happy I haven't made an error, so I'll just quit from there. And to find the mean and median, I'll go Stat, Calc, one variable Stats. Now the default is it will use the data in list 1. I'm not going to use the default. I'm just going to tell it list 1. So to put list 1 on the screen, it's second 1. The second key and then a 1. And it will use the data in list 1. So when I do that, I see the mean is 5, and the median is 3. So the mean is 5, the median is 3. So in this particular case, the mean is 5. Well, if I reorder these values are 1 and 2 and 3, 4 and 15. Those are the values, right? So because 15 is so different from these other 4 values, 15 is like an extreme value compared to the other data values, so that pulls the mean to the right, which is why the mean of 5 is bigger than the median of 3. 3 is sort of more on line with these values. It's like a middle value for those values. 5, which is the mean, is affected by this this extreme value 15. So that's what I can say about the mean and median for that example. Now in this second example, the numbers on jerseys of the starting offense for the New Orleans Saints when they last won the Super Bowl, and here's the data. Now numbers on jerseys, that's not a variable that has a level of measurement that we can use for mean and median. The numbers are just not meaningful. This is like a categorical variable. These numbers aren't meaningful for the players. They could just as well be, A, B, C, D, E, F, G, or some binary number. It's not meaningful. So since it's not meaningful, this data, it doesn't have the right level of measurement. We won't be computing the mean and median for this data. The numbers on jerseys is for football teams, it's like categorical data, similar to something like a zip code. A zip code, you wouldn't find a mean and median for a zip code either. It's not. It's like categorical data. Okay, so that's what I can say about that. Now here in your notes you have the instructions for how to find the one variable stats for the data. I've done it a few times now. If you need to refer to this, it's here. Okay, so here is another data set. This is the length of time in years it took for a random sample of college students to earn a bachelor degree. Based on these results, does it appear common to earn a bachelor's degree in 4 years? Okay, so I'll look at, well, what do I see? There are a bunch of 4s in the data set, but then all the numbers in the data set are bigger than that. right? There's 6 4.5s, a few 6s, some 7s, 9s, 13s, and a 15. So the length and time for, you know, these, I mean, it's a very small sample, but 4 is really the minimum here. So, and 4, well, it's not even the mode actually. There's 2 modes here. 4 and 4.5 are both modes because they both occur 6 times. But does it appear common to earn a bachelor's degree in 4 years? Well, if this is the data set, I don't see how it can seem so common, because it doesn't really occur very often. It is a mode, but again, there's so many numbers that are bigger than that number. Let's look at that data set. We'll look at the mean and the median for that data set. It'll take you a few minutes to put that data into your calculator, so you can pause and put it into your calculator. I did already put it into the calculator before I started this video, so it's already here. It's in list 2. So if I want to look at the one variable stats again, to get a previous command line, you can just hit set and enter, and so I have my previous command line. I don't want to find one variable stats on list 1. This data I put in list 2, so I'll change that to list 2. And I see the mean here is 6.5, which is not so surprising because, you know, a good percentage of the data is much bigger than 4. And also 15 is much larger than 4. So this extreme, and there's actually, these are all, you know, on much larger. So these values will pull the mean to the right. So the mean is 6.5. I suspect the median is smaller than that, which it is. The median's 4.5. So which is kind of interesting. You know, I'm tempted to look at a picture of this data. I didn't put it in Excel, but I am tempted to do a plot of it. Let's see, if I do a stat plot, and I put this on, and I want to look at a histogram of the data to look at the shape. And the data's in list 2, so I'm going to put list 2 here. And frequency is 1. Now I need to look at the window. So the window, well, the minimum x value is 4. So let's see, 4, so 4 to 15. Let's see, the difference between them is 11. So if I had 5 classes, there would be 2 in length. So the first class, x min would maybe start at 4, and x max would end at 16, and then I would have a step size of 2. And y, let's see, would start at 0. That would be 0 frequencies, would have nothing in a class. And 10 is, well, 10 might be okay. So if I look at the graph, there's more than 10 in this first class. So I need to change that. So, oops, I have to go back to window. So the y max here should be bigger than 10. So let's try 15. So the graph looks like this. So, I mean, this is the histogram. So you can see it has a, you know, a long, it's right skewed. Right? You can see this long tail on the right side. So does it appear common to earn a bachelor's degree in 4 years? Well, that's a funny question to ask. It is a mode, and it does happen, but again, there are a significant number of people for whom the bachelor degree is not earned in 4 years. So I would say that it's not so common. Not so common. Based on this shape, which has a significant number of individuals to the right. This is 6, by the way, not 4. This says earn a bachelor's degree in 4 years. My min was 4, this class is between 4 and 6. So 4 is not so common in this case. So that's what I would say here. And for the one variable stats, the median is larger than 4. Oh, and the mean is larger than 4 as well. So I would say no. Okay, that's that. So now we go on to the next example. And the next, it's sort of a mini topic here, the weighted mean. Now the weighted mean, the data values here are represented by this lowercase x, or the xi. Those are the data values. The w's are the weights. So if everything's equally weighted, then w would be 1, and this would just reduce to the regular mean, because you would have 1 times each observation value, and then in the denominator you would divide by the number of observations. So if you have 1 associated for each observation value, then this wi would in effect count the number of observations. So if everything's equally weighted, this is the same as the regular mean. If things are not equally weighted, then this formula will give more weight or more emphasis on values of higher weight. So in this example, this is an example using a weighted mean, and the example is GPA. So what happens in this example? A student's final grades, along with the number of credits for each course, were A in a 3-credit course, A in a 4-credit course, B in a 3-credit course, C in a 3-credit course, and F in a 1-credit course. Compute the student's GPA, noting that quality points to letter grades, well, it should say 4 letter grades, are as follows. So A is equivalent to 4, B is 3, C is 2, D is 1, and F is 0. So these are, so if we take a look at this, the weights in this class, the weight is by the course credit, okay? So that's what weights, that's the weight in a GPA. So if you have an A in a 4-credit course, that's going to have more weight on your GPA than the F in the 1-credit course. So to compute the weighted mean here, the letter grades are replaced with their numerical equivalents, and then to do this calculation, we're going to have the credit value times the grade in the course. So the data here are the grades in the course. This is the A in the 4-credit course, the A in the, excuse me, I said the wrong thing. Let me try that again. This is the A in the 3-credit course, A in the 4-credit course, B in the 3-credit course, C in the 3-credit course, and an F in a 1-credit course. And then these other numbers are the credits, okay? And then those credits are summed in the denominator. So in this case, the student's GPA is a 3.07, okay? Now, we're going to go through this process of how to do this calculation. So let's see what it is. Well, we're going to go stat and edit, and then what happens is in one column are the weights, and in the other column are the grades. So let's see, this first column is the grades, because this last one is the F in the 1-credit course. So list 1 represents the grades, which in this case are the X values. Those are the data values. The weights are in list 2. Okay, so we put the data in list 1 and then the weights in list 2 here. Okay, and then we'll quit. And then we'll be able to do this calculation in a single step by using this command on sum. So this sum sums the elements in a list, and what we'll do is we'll take the items in list 1, multiply by list 2. When you multiply lists, it does it component-wise. So if we take list 1 times list 2, the first entry in list 1 will be multiplied by the first entry in list 2. And the second entry in list 1 will multiply the second entry in list 2, and so on. So that's how this operation works, list 1 times list 2. And then when we add them up, we're actually doing this. That's the summation. Okay, so this is the sum of the product of the two lists divided by the sum over the weight list. The weights in this case are in list 2. Okay, so that's how we're going to do the calculation. So now we have another example here, and we can do this. We can do this together. So where's my calculator? My calculator's here. Okay, so we've got to turn it on. Go to stats, and I'm going to go to edit. Now I have data in here from the last two examples. I'm going to get rid of the data. To get rid of the data, the thing to do is use the up arrow to highlight the list. See, I have list 2 highlighted here, and then I'm going to press clear, not delete. Delete would be wrong. If you press delete, you actually delete a list, which is not a good thing, and I think is just something they should have fixed in these calculators a long time ago. But I don't think they have. So you can actually delete a list. So clear is the way to go here. Okay, so I cleared out the list, and well, what did I decide I was going to do? Who's in list 1, who's in list 2? I think I put the, let me just check how I was going to do that. The weights are in list 2. Okay, fine. So the weights here are the credits. So the credit values are actually going to be in list 2. So the credits for the courses, stat is a 3-credit course, intro psych 3 credits, bio is 4 credits, and phys ed is 2 credits. And then we'll put the grades in list 1. Now A is worth 4, C is worth 2, B is worth 3, and D is worth 1. Okay, so here's the grades, and these are the data values. These are the XI's in the formula, and then here's the weights. Okay, so let me get rid of all that. Okay, so to do the weighted mean, then we want to go to do the summation. So the summation, if you go second stat to list, list is, this is here. We want to go over to math, and sum is the 5th option. So if we sum, we want the product of list 1 times list 2. And so that's going to be the sum of xi times wi, the data values multiplied by their weights, and we'll be adding those up. And then we want to divide that by the sum of the weights. So the weights are in list 2, so we've got a sum on list 2. So if we go back to second stat and over to math, sum is the 5th item in the list, and we'll sum on list 2. Okay, so here's the GPA. In this case, it's about 2.67. Okay. Okay, so that's that. Okay, so shape is an important feature of data, and this was something that we spoke about maybe a few times. Data that's symmetric and bell-shaped would look like this. And in this case, the mean, median, and mode are all the same value. But the bell shape is an important shape in statistics, and we're going to see that again later on, even today in this talk. This is a very key shape. Sometimes we have something that's a little off from that. That's where the skews come in. In a left skew, there's a longer tail on the left side than in the symmetric case. And in a left skewed situation, the mean is pulled to the left because these values are much smaller, and those will have an effect on the mean because the mean is the sum of all the values. So very, very small values will make the mean smaller. The median will be to the right because the median is going to be the middle value. So that is unaffected by these very small values. Right skewed is very similar, except the longer tail is on the right side, and these larger values will pull the mean to the right. Okay, another, okay, so range, this is a measure of dispersion. This is spread, variation. So range is one measure of spread, and the range is just the max minus the min. It's the largest value minus the smallest value. The thing about the range is that it doesn't give you any clue about how the data is distributed. So if you look at these two examples at the bottom of the page, in both cases the range is 3, right? 10 minus 7 is 3, so max minus min is 3 in both cases. But the distributions are very different. This distribution or spread for the data is called uniform because one value is not favored any more than any other value. This distribution for the data wouldn't be called uniform, right? What would we call this? So hopefully you said left skewed, right? Because the skew is over here, and it would be like that, okay? So the range is, of course, going to be sensitive to extreme values, and it's not going to be used as much as the standard deviation. So standard deviation and variance are very, very useful, particularly the standard deviation. This is a measure of spread. It's a very common measure of spread, and this will give us some clue about how the data is distributed. This is exactly a measure of how much the data on average deviate from the mean. So we have the data, this picture, the data is sitting on the set of real numbers. There's a little fulcrum here. The mean is the balancing point, right? So if each of these data points weighed the same amount, they're all equally weighted, if you put a little fulcrum on this scale, these would be perfectly balanced, provided this fulcrum's at the mean. So the variance is going to take the squared distance from each of these points, the squared distance from each of those points to the mean, and take sort of an average. It's only sort of an average because if you look at the formula for the sample variance, we're not actually dividing by n, we're dividing by n minus 1. Turns out that if you divide by n minus 1, it's a better estimate of the population variance than if you use n. The population variance you do divide by capital N here is the sample size. So the notation for the sample variance and population variance is different. For the sample variance and standard deviation, a lowercase s is used, and for the population variance, the Greek letter lowercase sigma is used. So the standard deviation is just the square root of the variance. So here's the variance calculation for a sample, and the standard deviation calculation for the sample is the square root of the variance. And similarly for the population variance. So we'll use a calculator for these, but it is useful, you know, just to see how these calculations are made. So here's a quick example. Here's 4 data values, and the mean for the data values is 23.5. So the sample standard deviation here is this formula, and what it means is we're going to add up the squared distances of each of the points from the mean. So each of the data points, subtract the mean and square those. So those are the squared distances. And we're taking almost an average. We're dividing by n minus 1, which, as I mentioned, is a better estimator for the population standard deviation than just dividing by n. So in this case, the sample standard deviation is this value. Okay, so now we can talk about what are usual values. Usual values using standard deviations would be values within 2 standard deviations of the mean. So that means the smallest usual value would be the mean minus 2 standard deviations, and the largest usual value would be the mean plus 2 standard deviations. Now, to use the, if you take a look in your book, there's something called the range rule of thumb, and the range rule of thumb is an estimate of the standard deviation. So if you just wanted to do a very rough guess of what the sample standard deviation is, you could roughly guess it as the range divided by 4, where again the range is the max minus the min. Okay, so here's another data set, and we need to find the measures of center and spread, and find the range rule of thumb and compare with the standard deviation. Okay, so it can take you a few minutes to do that. I have that information here already. You should find the mean and the median are here, which are very close in value to each other. There's a few modes. Obviously the mode is not unique. You can't get this from your calculator exactly. You have to, you'd have to do this either by eyeballing it and just looking in the data to see which values are most frequent. Now the standard deviation is 0.82, and the range rule of thumb, what does that give us? So the range rule of thumb is going to be max minus the min, which in this case is 2.6. When you divide that by 4, you get 0.65. So the range rule of thumb underestimates the standard deviation in this case. And here's the screenshots. This data is almost symmetric, and that's evidenced by these being almost equal. It looks like there's a slight pull to the right, which a slight right skew here, and you can also see that because the mean is larger than the median. Okay, so here's something that maybe when we get back to class we'll think about doing this. Estimating the average male and female heights, which doesn't seem like that difficult an activity. Estimating the standard deviations, though, seems like a much more difficult activity. So you might think about how you could do that. Estimating the male and female heights using the range rule of thumb, and we can. And this is definitely has to be a class activity, because we'd have to see what you came up with to see who did the best job with the estimates. Okay, so now we're up to the empirical rule. So the empirical rule, there's a link on Campus Cruiser for empirical rule, and I would like you to please take a look at that link. That gives a very detailed explanation for the empirical rule and goes through some examples as well. So please take a look at the video that I provided for you on empirical rule. And so when we come back to class on Thursday, we'll do this example and this example, but I'll assume that you have looked at the video on using empirical rule. Now what I'd like to jump to at this point, well, is we can mention about the coefficient of variation, and then we'll talk about z-scores. So the coefficient of variation allows you to compare variation for different samples, for different variables, for example. So the coefficient of variation gives you a percentage of the variation, and you can compare two items that are dissimilar. So for example, in this particular example, the mean waiting times in an emergency room is 80.2 minutes with a standard deviation of 10.5 minutes for people who are admitted for additional treatment. The mean waiting time for people who are discharged is much larger, 120.6 with a standard deviation of 18.3, which times are more variable. So, I mean, hopefully you've never been in an emergency room, but if you have, you know that they triage in an emergency room, and people who are considered more urgent need of care are seen first, right? So people who need additional treatment, I suppose, are those people who are in need of more urgent care. So they have a smaller mean and standard deviation. So which are more variable? Well, we can say the coefficient of variation. Let's see, what is the coefficient of variation in each case? So for the discharge patients, it's this value. We would take the mean divided by the standard deviation, and then no, I said the wrong thing, I apologize. This 10.5 is for the patients who are going to be staying in the hospital for more treatment. So for the patients that need more treatment, the coefficient of variation is smaller than for patients who are discharged. So there is more variation for the patients who are discharged, because this coefficient of variation is a bigger number. It's 0.15 as opposed to 0.13. Okay, so now we're ready to talk about the Z-score. So I also put a video for you to look at for Z-score. They do a perfectly good job of explaining Z-score and discussing Z-score. So I'd like you to take a look at that video on Z-score, and after you've looked at that video on Z-score, then we will look at this example when we meet again on Thursday. So you got to remind me, when we meet on Thursday, I want to do this example and this example, the two examples from empirical rule, and I also want to do the Z-score example. And then we will be still needing to do the percentiles, but I think I am going to stop here for now and continue with percentiles on Thursday. Now, so what do you need to do? Well, you should be working on the Chapter 3 problems on my Stat Lab, and I'm also putting up for you on Campus Cruiser a review for your first exam. Your first exam will go up to but not include percentiles. So this topic will not be on your first exam, percentiles. It will be on your second exam. Your first exam will go up to and include Z-scores. So it will be the first two chapters and part of Chapter 3 up to and including Z-scores. So I will put some old exams on Campus Cruiser for you to take a look at, and then you have some additional work at my Stat Lab, and you also have, you should be preparing your cheat sheet because your exam is on Monday, October 5th, and you have the videos to look at on Z-score and empirical rule. So, get to work, and I'll see you on